Good evening, ladies and gentlemen. Can you please rise as the procession enters the room?
Right, good afternoon, everybody. You may be seated. So my name is Wickert van Niekerk. I'm currently the Dean of the Faculty of Engineering, and it's really a pleasure to welcome all of you here in person, and then also everybody that's online. You are part of this wonderful event, so thank you very much for dialing in. We are blessed that we have 3 members of directorate who are joining us. So Professor Nicola Smit, who is the Acting Chief Operating Officer, and just because she thought that was not enough, she also added now the Acting CFO, or Chief Financial Officer as well, so she's got 2 jobs. Do they pay you double? We also have Professor Sibusiso Moyo here, who is the DVC Research, Innovation and Internationalization, and then also Professor Liesel van Dijk, who is the new DVC academic. Of course, we have Professor Japie Engelbrecht here, who is our honorary speaker and really the person around this whole event. So Japie, welcome here. We want to also welcome his family, which is his wife Marjorie, their children Amay and Mira. So welcome that you are here as well. And then also Professor Japie Engelbrecht Senior, who is also here. And as you see, he's also an academic, or he's an emeritus academic. So baie dankie dat jy saam met ons hier so kan wees. Then also Ans Jacobs, the mother-in-law to Professor Engelbrecht, and Ans is online. Then also brother and sister-in-law Herman and Marianne. So Herman is also sitting right here, and also their children who are here. Then brother Skalk, who is here as well. Brother-in-law and their wives Andre and Inyong, who are here. And then also Hugo and Boram joining online from Korea. So welcome to them. And then you had a hard time, Japie. You had 3 supervisors, right? Professor Herman Steyn, who is here. So Herman, baie welkom by ons. And then also Dr. Thomas Jones, who is here, and Dr. Ian Peddle. And then old friends from the university days in the Electronic Systems Laboratory, and that also includes some other colleagues as well. So for instance, Professor Martin Kamper, who is here. There were old colleagues from the Sunspace days. Then colleagues from S-Plane, past and present, previous students, other colleagues in E&E and the rest of the Faculty of Engineering, friends, collaborators, students, and all the others attending in person and online. So now everybody in this room and online should feel welcome. I also have to tell you that there are some house arrangements that you should be aware of, so please make sure your cell phones are either switched off or they are on silent. If you need the facilities, if you go out this door on the left-hand side, we apologize that they don't have doors, but the doors will come. So next time you're here, hopefully there will be doors. And if in an emergency, there's an emergency exit down there. You go down to the stairs and you exit at the bottom, or if that is available, you can also exit through that way. Then it is my pleasure, really, to introduce Professor Engelbrecht, Japie Engelbrecht. So I've got to say, we've got 2 professors. Well, I've got 3 Professor Engelbrechts in the room. So Professor Japie Engelbrecht to you. So he was born and raised in Port Elizabeth, but now it's called Kuberka in the Eastern Cape. He enrolled at Stellenbosch University right after matric, where he went on to complete his bachelor's in engineering in electrical and electronic engineering in 1997, as well as his master's in 2001. under the supervision of Professor Jan du Plessis. Now, if you don't know who Jan du Plessis is, you can come and chat to me afterwards, but I think that must have been quite an experience, having Prof. Doep as your supervisor for that. And his master's thesis focused actually, and he was part of the SANSAT team. And those of you who don't know about SANSAT, that was the first satellite that was designed, built, and eventually launched from the African continent. So that is really, you were part of history at that time. It was launched in 1999. And I inquired the other day, apparently it's still up there, right? It hasn't come down yet. Sumdabila-sat, I think they said it came down, but I think they think SANSAT is still somewhere up there. In 2002, he joined the spin-out company Sun Space and Information Systems, where he worked with Professor Herman Stein as a control systems engineer, developing attitude and orbit control systems for the Oryx, the Sumbandila sat, that's the other satellite that was launched from the, built in Stellenbosch and then launched in the US, as well as the Oryx 2 satellite. He returned as a senior lecturer in control systems to the university in 2008, where he shifted his research focus to aeronautical applications, including flight control systems for large commercial airlines developed in collaboration with Airbus, and autopilot systems developed with Armscor. He also started consulting as a part-time systems engineer for S-Plane Automation, another company that is sort of a spin-out from Stellenbosch University in some sense, because of course, you were the instigator of that venture, which is doing really, really well. He also developed subsystems of unmanned aircraft systems and optionally piloted. I have a hard time understanding that, but I think you're going to tell us what optionally piloted means, right? As a mechanical engineer, I don't want things to be optionally piloted. I want it to be piloted. Optionally piloted systems, and he completed his PhD at Stellenbosch, and in 2016 under supervision of Professor Thomas Jones. Then he was promoted to associate professor in 2022 and full professor in 2024, and is currently the chair of the Department of Electrical and Electronic Engineering. Over the course of his career, he has enjoyed teaching control systems, supervising final year projects, and postgraduate students, and he collaborated with colleagues in industry and partners to develop control systems for satellites, aircraft, drones, electrical water heaters, and a bunch of other stuff. He's married to Marjorie, and as you heard, they've got 2 daughters, Amay and Mira. And the last piece I want to just share with you, because I only learned it this afternoon. Apparently, he takes after his mother, and he really cares about people, right? And I can attest to that. So whenever we make a decision in the faculty management committee, and it's a bit, bit harsh, he says, no, we can't do that. What about the people? So Japie, ek verstaan nou presies hoekom jy my so gas gee in die komitee, en dis wonderlik om na jou ma te aard. The floor is yours for your address.
Okay, let me just quickly make sure I don't type in my password incorrectly 3 times, because then it's going to be a very short inaugural lecture. Okay, looks like I'm in. Just change this. Okay, thank you, Vikas, for that kind introduction. Welcome to my inaugural lecture. I really appreciate everyone who came out to support me in person today and who are joining online. I'm very humbled by all the messages that I've received from people who this advertisement has done the rounds and has been WhatsApped everywhere. So I've received messages from people I didn't even realize, and that really humbles me. And it is my honor to share with you, hopefully today, my love of control systems, why I think it's magical, and then also tell you a little bit about my career so far. Herman Kamper, who is somewhere, yeah, there you are, Herman. He told me, you know, everybody stresses about their inaugural lecture, and he said I should treat this as my birthday, and I should enjoy it. So I'm really going to try and enjoy it, and I hope that you will enjoy it with me. Okay, so just to tell you what to expect from this lecture. So first, I'm going to show you 2 demonstrations of very simple control systems, but which were basically the demonstrations that showed me the magic of feedback control, and is probably the reason why I'm standing here today. So I do realize that sometimes things that seem magical to engineers are not so magical to other people, but I'm going to try and hopefully you will share a little bit of that wonder with me. Then I'm going to ask the question, what is a feedback control system? And I'll answer that using 2 examples, a very simple example that we all have in our homes, and then a more complex example. Then I am going to give you a crash course in feedback control. Now, I know this is a little bit ambitious, but I really thought that I would try to show you the other part of the magic of feedback control, which is the wonderful mathematics that we have to design feedback control systems. So I'm not going to expect you to understand it. I'm going to ask you to think of it as if you are watching your favorite medical drama, you know, House or Scrubs or Grey's Anatomy. You don't understand all the terms and terminology, but you can follow the story. So I hope that's what I will achieve now. Then that will be the lecture part of the inaugural lecture, and then I'm going to give you a brief history of my control systems career, highlighting some of the interesting projects that I worked on, and finally I will reflect a little bit on the opportunities that I had, the mentors that I had, the colleagues that I worked with, and especially the students who I taught and supervised, and who in effect taught me while we were doing that. So that's the plan. Now you heard there was a very long welcome, and there's going to be a very long vote of thanks at the end, and that's my fault. And I have a little bit more slides that I'm really comfortable with, so I'm not sure it's going to be 45 minutes. If I see people starting to move around uncomfortably in the seats, I will skip to the end, so don't worry. Okay, the magic of feedback control. So the first system I'm going to show you is a robotic arm that balances a pendulum. So the robotic arm can just move backwards and forwards. The pendulum is swinging freely, and then the control system moves the arm back and forth in such a way that the pendulum swings up, and then it balances it in the upright position. And this is not actually the system that made me interested in control systems. The specific one was one that Herman Stein built, that had a whole cart moving along a railway with the inverted pendulum. But this is the closest thing that I could find a video of that I could show you. So here we go. There's the robotic arm. Here's the pendulum, and you'll see what it does. So it swings it back and forth, and then in the upright position, it keeps it upright. And it's doing that because it's measuring the upright position. It's measuring the angle that the pendulum is falling, and it's reacting by moving the robotic arm back and forth like you would do if you were balancing a broomstick on your hand. Then the next system I'm going to show you, which illustrates really the thing that is magical to me, is what's called a ball-on-beam system. So what you will see, maybe I can show you the picture before the video starts, no I can't, is a beam with a ball bearing on it, and the control system can actuate the angle of that beam. And if it tilts the beam, then the ball rolls one side, and if it tilts it the other way, the ball rolls to the other side. So the ball is just moving under gravity, and what the feedback control system is told to do is to move the ball to specific positions on the beam. So it will be told, move left to this position, move right to this position, or move to the middle. And the beam is going to move, tilt it to make the ball roll, and then tilt back up again and stop the ball and stop it at the right location. And the other thing it's going to do, and this is really the magical part, is a person is going to disturb the ball. They're going to tap the ball to move away, and the control system is going to react. It's going to tilt up and bring the ball back to where it was commanded to be. So to me that's magical, because the system reacts like a living thing. because it sees this disturbance and reacts to it. So let's hope it's as impressive as I like described it now. So this was a Scripsy student of mine in 2010, so that's why the video quality is a little bit poor. But you can see it's being told, move the ball to the right marker, move the ball to the left marker. And it tilts, lets it roll, and then tilts back up again and stops it. And it does it. This is kind of called the step response of the feedback control system. Now here's the disturbance rejection. So it's told to keep the ball in the middle of the beam, and when the person disturbs the ball, it senses that that ball has moved away, and it reacts to bring the ball back to the middle. Okay, and here is just, here is just doing it more aggressively to show how the system responds. So there's a little computer that's measuring the position of that ball and commanding the motor that tilts the angle of the beam. And here it just shows how accurately you can move the ball to that position. Okay, I'm going to stop here. So that's what attracted me to feedback control systems. So what is a feedback control system? It is a system of sensors, control algorithms, and actuators to control the output of a dynamic system to follow some commanded value. And here is our general feedback control block diagram, which I'm not going to talk through now, but which I will talk through a little bit later when I give you the crash course. So here is a simple example which you all have in our home, a hot water geyser. So the system that we want to control is the geyser. Actually, let me move a little bit here. Is the geyser. The output that we want to control to a certain value is the temperature of the water. The way that we can change the temperature is through the heating element, which we can switch on and off. And then there is some temperature sensor that measures the water temperature. So what the feedback control system does is it measures the water temperature, it compares the water temperature with some set point, and then it switches the element on if the temperature is too low, and it switches the element off when the temperature is too high, and we put a bit of tolerance there. We say if it's below 55 degrees, then we switch it on, and if it's above 65 degrees, then we switch it off, and then that temperature moves between the 2 points, and we get an average water temperature. But it's like measuring the output and then adjusting the input to control it to follow the set point. Now here's a more interesting example which Prof. Jones will recognize. The original Slade, not the quadrotor Slade, the counter-rotating ducted fan vehicle, which is basically an engine with some flaps at the bottom. And this is now the complex system that we want to control. The sensors that we use, the outputs that we want to control is the position of this vehicle, its speed, its translational speed, its orientation, and its angular rates. The sensors that we use to measure those outputs are a GPS, angular rate sensors, accelerometers, a magnetometer, and the actuators we have is we can control the speed of there's two propellers inside that we can control the speed of, and there are flaps here that we can use to direct the thrust of that's coming out of the engine. And what we then achieve is that we can tell this vehicle to go to certain positions, to fly from one position to another position, or to navigate some waypoints. Now I'm going to show you a very old video of that happening. Thomas, I'm not going to show you at the end. So it's taking off under piloted control. This is the parking lot at the back of the engineering department. It didn't used to be a parking lot. It was this green field. And what impresses me here is this thing doesn't look like it's supposed to fly. It doesn't look like it's supposed to stay upright, but it does. It hovers there, and when you tell it to move to another location, it tilts itself and it moves to that other location. And if we watch long enough, we'll see it stopping there. But I have many slides, so I'm going to go on. Okay, so what are the goals of a feedback control system? Well, the goals / advantages. The one goal is stabilizing a system. So, for example, that inverted pendulum system, it doesn't want to stay upright. It's an unstable system. It wants to fall down, so a feedback control system can stabilize it to keep it in the upright position. The second goal of feedback control is called command tracking. That's where you make a certain output follow a commanded signal. The third goal is disturbance rejection. That is to prevent the output of the system from reacting to inputs that disturb it, inputs that are not under our control but which affect the output. And then also robustness. So we design a feedback control system based on a mathematical model of that system, but our information is incomplete. We have a limited model of that system, and also the values of that model might not be exactly what we thought it was, or it might change over time. So our feedback control system gives us robustness to these changes in the actual system that we're controlling. Some important bits of terminology that I just have to establish with you. Stability, what do we mean with stability? A system is stable if its dynamic response eventually reaches an equilibrium, or stated differently, if I disturb a stable system from its equilibrium, it will return to its equilibrium. While a system is unstable if its dynamic response grows monotonically or oscillates with an increasing amplitude. Or stated differently, if I disturb the system, it won't return to its equilibrium. It will run away, either directly away or, oscillating away. Mathematically, it will go on to infinity. Physically, it will break. If it's an aircraft oscillating up and down, the ground is eventually, the limit there. So, okay. So another important, just 2 bits of terminology I need to establish is when a control system controls the output to go from one desired value to another desired value, it has a transient response. So it has a way of getting to that final value. And that can be, it can get there slowly, it can get there quickly. It can get there sluggishly, or it can oscillate while it goes there. So we want to know how a system, what its transient response looks like, and we also want to be able to change that transient response to be like we want it to be. The other important piece of terminology is steady state error, which is after the transient, when it reaches its new set point, how far is it from where you told it to be? It's now at a constant value, but it might not be at exactly the value that you want it to be, and that's called steady state error. Okay, the anatomy of a feedback control system. So we start with the system that we want to control, and that's called the plant. It is some dynamic process, which is a process that changes over time, and we want its output to follow some reference, some set point. We have an actuator which can affect that dynamic system, and a control signal that we can provide to move that actuator. So I actually should have used an example here. So the plant could be something like a car. The cruise control of a car, we want to control the speed of the car. And how can we affect the speed of the car? We can step on the gas. So we can increase the force applied to the car or reduce it. Or that system could be an electric water heater, where the output we want to control is the temperature, and the actuator is the heating element that we switch on and off. So, in control system terms, any dynamic system we want to control is called the plant. And it comes from chemical engineering and chemical processes where feedback control is applied there. Okay, so often we have this disturbance which disturbs the plant and makes the output behave in an undesirable way. What we do is we add a sensor to measure the output, and then we get the measured output. That sensor often has sensor noise, which corrupts our knowledge of the output. And we subtract that measure output from the reference, and the error signal is how far our output is away from where we want it to be. And then our job is to design a controller that uses the error signal to decide what to do with the control signal so that the output follows the reference signal. Okay, so we want typically that error to go to 0. When the error is 0, it means the output equals the reference. If we can't make it go to 0, we want it to be very small, preferably. Okay, and disturbance rejection is the controller must minimize the effect of the disturbance on the output, and that is called disturbance rejection. Our sensor noise makes that we can't make this controller infinitely aggressive because we want the controller to react to actual errors in the output, but we don't want it to react to imagined errors in the output, which is due to the sensor giving us incorrect information about the output. So that limits how aggressive we can make the controller. Okay, what do I mean with closing the loop? This is also going to be important for the crash course. So our open loop system is the system that we are given to control. So, or rather, let's say our plant is the system that we are given to control. We haven't added anything to it. It has an input and an output. We then add to the system a controller and a sensor. Those three things together, the system that has the error signal as the input and the measured output as the output, is called the open loop system. And then when we close the loop, this is called the closed loop system, and it has the reference signal as the input signal and the output signal as the output signal. Now, why this is important is we are going to start by modeling the plant and getting a mathematical model of it and analyzing its behavior. Then we are going to add a controller and a sensor, and then we would like to know what will happen when we close the loop, because if we don't know what's going to happen, we might get undesirable behavior and we could break our system. So this open loop system is a mathematical intermediate step that we use to predict what happens to when we actually implement our feedback control system. We never operate it like this. We use it as a tool, a stepping stone to our closed loop system. Okay, now we get to the hard part, the mathematics. Okay, so when you design a feedback control system, there are basically 5 phases that you go through. The first one is you decide on the specifications. What do you want the feedback control system to do? Then you model the system. You mathematically model your dynamic system. Then you analyze whether that system is stable or unstable and how its transient response and steady state response looks like. You then design a controller to change that transient response and steady state response, and that has 2 steps. You choose a controller, and then you calculate the values, the appropriate values for that controller. Then you go and test it, and before you test it on the physical system, you first make a computer, like a flight simulator simulation of it. You check that it works on the flight simulator, and if it works on this flight simulator, only then do you go and test it on like the physical aircraft, so that you don't go directly to the aircraft and cause a lot of damage and cost a lot of money. Okay, so how do we mathematically model a dynamic system? We use the wonderful mathematics called differential equations. So differential equations, this is one of those terms from the medical drama, right? It's the differential equation. Okay, so these are equations that tell us how the variables of a system, what the rate of change of the variables of a system are as a function of the variables themselves and other inputs to the system. So we will have some system like a car or a aircraft or an electric water heater, and we will write down the differential equations that describe the behavior, mathematically describe the behavior of the system. And then we can solve those differential equations for given inputs to see how will it respond to this input, how will it respond to that input, or we can use a computer to numerically solve and see what the behavior is of that system. So, and then we can design our feedback controller. Okay, so now this is the most mathematics that's going to be in this presentation, but I really want to share this with you. So I'm going to take a simple system. Here is my little hand-drawn car. I want to describe how this car moves under the influence of the gas pedal, the force applied by the gas pedal, but also under the influence of the air friction that acts on the car. So I start by saying, to describe the motion of this vehicle, I need to know the position, the velocity, and the acceleration of the car. So in high school terms, we would call those X, V, and A. But in differential equation notation, we call it x, x dot, and x double dot. The dot means rate of change. So x is the position, x dot is the rate of change of the position, and x double dot is the rate of change of the rate of change of the position, i.e. the position, the velocity, and the acceleration. So I want to set up an equation that has x's, x dots, and x double dots, and that is called a differential equation. How I do that is I apply Newton's law. Force equals mass times acceleration. The acceleration of this vehicle, the x double dot, equals, well, multiplies by the mass, equals the sum of the forces applied to this vehicle, which is the engine gas pedal force and the air friction force. So here is the gas pedal force, and the friction force is proportional to the speed at which the car is moving. So F gets replaced by U minus BX dot, and I've sneakily replaced A with X double dot. So now I've got equations that are just in terms of X double dot and X dot, and I rearrange it to eventually get something where I have the highest number of dots on the left-hand side and the lower numbered dots on the right-hand side, and that is our differential equation, which describes the motion of this vehicle, and which I can now use as the basis of a feedback control system, a cruise control system that controls the speed of this car. Okay, so I'm not going to derive this. I'm just going to show you we can derive differential equations for other systems. This is the differential equation describing the rotational motion of a satellite. This is the differential equations describing the voltages in an electronic circuit that has a time-varying voltage applied and some capacitors and resistors in there. These are the differential equations that describe how an electric motor reacts to a voltage applied to it. And now I'm going to show you like a very big system. So those are all simple sets of differential equations. I can model the motion of an aircraft flying through the air under the influence of gravitational forces, aerodynamic forces, and thrust forces. And those equations look like this, this, and this. Okay? So I can write down a lot of mathematics, and then I can simulate. I can build a flight simulator, or I can solve some mathematics and see how this aircraft will move. Okay, now I have the mathematical model. But just looking at those equations, you can see they look a little bit Greek. So, and it's going to get more Greek. I want to know, is this system stable? Is it unstable? And how does its transient response look? So what I do is I transform these differential equations into transfer functions using a mathematical operation called the Laplace transform. So for the physicists here, Laplace transform is similar to a Fourier transform, it's just better. For the signal processing people here, the Laplace transform is better. Okay, so I get this new format called a transfer function, and the transfer function tells me the relationship between an output and an input, but it also gives me information about the system's behavior. So I can look at the poles and zeros of the transfer function, and it tells me about something about the stability of the system and the transient response of the system. And this transfer function I can also use to find out what the steady state equilibrium values will be if I change input from one value to another value. So what are poles and zeros? I can write my transfer function as a algebraic equation on top of an algebraic equation. This is high school mathematics. I can factorize them, that's also high school mathematics, and then I get, again, zeros and poles. And I can plot them in a special complex plane called the S-plane, which is also the name of a company in Somerset West. So if I, for example, if this is the transfer function of my system, and these are the poles, and that's the zero, the crosses are the poles in the complex plane, and the zero, the circle, is the zero. And as a control systems engineer, I can read this plot, and I can tell you, this is an unstable system which has some oscillatory behavior and also some stable decaying behavior. Because I know that if the poles are in the left half plane, the system is stable. If they're to the left of the line, the system is stable. And if they're to the right of the line, the system is unstable. If they are real poles, then they have an exponential response, and if they're complex pole pairs, then they have an oscillating response. So this real pole in the left half plane, if I give the blue line as the input signal, I will get a red exponential response on the output. If the cross is on the right-hand side, then if I give a step to the input of the system, the output runs away to infinity. It's an unstable system. If it's in the middle, we call that marginally stable and just kind of like linearly runs away, which is still bad. Okay, if it's a complex pole pair, then it's stable. It'll end up with an equilibrium value, but on the way there, it will do this. And if this is your altitude control system, your passengers are going to get very uncomfortable, or if this is your suspension, also very uncomfortable. So if those are on the right-hand side, then the system oscillates, but with an increasing amplitude. So it's an unstable oscillating response. And if it's on the line, it's marginally stable and oscillating, so it's just a oscillation that keeps on going forever. So I can look at these poles and tell you how the system is going to respond. And actually what I want is I want the system to have the poles here with a 45-degree angle here. Then I get that beautiful response, which we call an optimal response, which is just having like a little bump and then going to the value that you want it to go to. Okay, so now we know how to analyze the dynamics of a component from the transfer function that we get from the differential equations. So I can now take every component of my feedback control system and represent it with differential equations, and then I can transform them into transfer functions, and then I can use a thing called block diagram algebra to replace all of these blocks with a single big block called the closed loop transfer function. So the closed loop transfer function tells me how the system will behave after I've implemented my control system, while the open loop transfer function, before I close this line, tells me how the system behaved before I closed my loop. So I'm going to use this ability to design a controller. I'm going to say my job is now, I have a plant transfer function, I have a sensor transfer function, I must design a controller transfer function consisting of, again, some poles and some zeros to make the closed loop system behave, to be stable and to behave in the way that I want it to behave. So how do I do that? I first choose a template. I choose a template transfer function for DS, and I choose it from families of controllers. The one family of controllers is called the PID control, proportional plus integral plus derivative control, and there's another family of controllers called lead lag compensation. Again, for the control systems experts among you, I'm only talking about classical control here. We're not talking about state space control and other kinds of frequency domain control. I'm just using classical control as an example. Okay, so we choose one of these templates, but we need to figure out what must the values be of these KP, KI, KD, K, Z, and P. And for that, we use the root locus plot. So what the root locus plot does is, if I have the open loop transfer functions, GS, HS, and some poles and zeros that I've chosen for DS, it tells me how the closed loop system's poles will change as a function of a value that we call the gain, K. And the closed loop poles tell me what the stability and the transient response of the closed loop system will be. So I am going to see how my gain changes the behavior and then choose the value of K that gives me the behavior that I want. So here's an example of a root locus plot. These crosses are the open loop poles, and the blue lines are how the closed loop poles will move as I select different values of that gain K. So if I have like a very low value for K, then what I should have said is the closed loop poles start at the open loop poles and end at the end of the root locus plot. So for very low gain, I can see I've got an unstable pole here, so my closed loop system will be unstable, which is bad. If I make the gain a little bit higher, then this pole moves onto the line. I get a marginally stable closed loop system, still bad. Now it's moved into the left half plane, so now my response is stable and exponential, but maybe a little bit slow. If I move it further, these two become complex pole pairs, and I get that beautiful optimal response. If I push my luck too far, then it starts becoming oscillatory, still stable, but oscillatory. If I push my luck even further, it starts oscillating indefinitely. And if I push my luck even further, it becomes unstable again, but oscillating instead of running away normally. So I use this plot, I draw this plot, and then I see, oh, this is the value that I should use in my controller. Okay, mathematics done. So, after I get this controller transfer function, I want to go and test it, so I build a little simulation where I implement that controller and I see how the system will respond. So here I've, in MATLAB, built a little simulation of the ball on beam controller, and here is an animation. So this is the open loop response. Open loop response means I just tell the beam to tilt and I leave it there, and then I watch what happens to the ball, and it just rolls off. Then I implement my feedback controller, and it does this. So I've made my simulation a little bit too bouncy, so you'll see the red ball will just jump up a little bit, but it is moving just like that original video from one point to a different point back and forth. So this tells me, okay, my control system has a good chance of working. Let's try it on the physical system. So just one step before I can actually try it on the physical system, I must now change this mathematical transfer function ds. I must change into something physical. And I can change into anything that represents those differential equations. That could be a mechanical system consisting of springs and dampers. It could be an electronic system. It could be digital software. These days, mostly we implement it as digital software. So here's an example of an electronic circuit that implements one of the controllers. Here is an example of software code that implements that ds mathematical transfer function that I designed. So I go and implement this, and then I apply it, and then I see, okay, my real system reacts similar to what my simulated system reacted and similar to what my mathematics predicted was going to happen. Okay, so before I go over to, that's now the lecture part done, but before I go over to that, I want to say that that control system design is only for one little loop. It controls one output using one actuator. But most of the complex systems that we're trying to control have multiple outputs that we want to control and multiple actuators with which we control it. So a real control system, we design lots of little feedback control loops, and we integrate them and use them together to control this whole complex system. Okay, brief history of my control systems career. So it started in 1998 when I joined the Electronic Systems Laboratory, and for the first part of my career I focused on satellites, on satellite attitude control at the Electronic Systems Laboratory and at a company called Sunspace. Here is a picture of the old ESL before it was moved to where it is now. So you see this carpet here? When I studied, it wasn't there. There were benches there. I was sitting there, and Gerard was sitting in the ground station close to me. So this is where it started. I did my master's degree under Prof. Du Plessis here. I was very fortunate to be there at the right place in the right time when Sunsat was, the development was finishing and it was launched, so I could participate in that. And I also made friends here for life, and many of them are here today to support me. Okay, so now I'm going to show you some real systems that I worked on. So first, I'm going to tell you about attitude determination and control of satellites. So why do we want to control the orientation of a satellite? Because we want to point its solar panel towards the sun so that its solar cells can charge. Arnold, you should appreciate that. And its batteries can charge using the solar panels. We want to be able to point its cameras at a point on the Earth so that we can take a picture of that place, and then we want to download that image to a ground station which is at a different place on the Earth. So we want the ability to control the orientation of the satellite. What makes it difficult is because we're using feedback control, we want to first determine the orientation, and how we do that is quite interesting. We use a combination of sensors. We use a magnetometer that measures the Earth's magnetic field, and we compare it to a model of the Earth's magnetic field. We use core sun sensors, little solar cells, to see what side of the satellite is the sun shining onto it so that we have a rough direction of where the sun is. We use this thing, which is a fine sun sensor, which basically takes a picture of space and tries to find the sun in that picture, and it tells us in what direction is the sun relative to the satellite. We have this thing called the horizon sensor, which takes a picture of the Earth and then determines where the horizon lies and uses that to determine what the direction of the Earth is relative to the satellite. And we have this thing called a star sensor, which takes a picture of the stars and matches those stars with known constellations and then determines what direction the satellite is pointing. Once we know what direction it is pointing, we can change the direction to where we want it to point. And for that, we use actuators, two interesting types of actuators. One is called magnetic torque rods. These are electromagnets that, when you energize them, they produce a magnetic field. They push against the Earth's magnetic field, and that causes a rotational force on the satellite. So you can apply forces to the satellite by switching on electromagnets which are pointing in different directions. The other thing we can do is we can use reaction wheels. We have these 3 wheels that are also pointed in 3 perpendicular directions, and they exchange their momentum with the satellite. So if we slow down the reaction wheel in the one direction, the satellite speeds up in the other direction. So we can control the speeds of those reaction wheels to effectively control the rate at which the satellite is turning. And these 2 things, and there's another one which we didn't have on some Manila sites, you could have little attitude thrusters. You could have like thrusters that just spew out gas, and that causes a moment on it. So, now I'd like to show you a short video, so I'm going to dim the lights. So this is a simulation of the Sumandila satellite and the attitude control that is applied to it. So initially the satellite, when it's released from the launch vehicle, it's tumbling, and we need to get rid of the tumbling. So the magnetic torques fire in certain ways to reduce the tumbling of the satellite, and it also starts making that satellite tumble in a forward motion at a specific rate. And when it does that forward tumbling, that's called a Y-Thomson spin. Once we have that spin, the satellite is now kind of like stably spinning about a certain axis, and we now want to tilt that spinning axis so that it points towards the sun, so that our solar panel gets the most sun, so that the batteries can charge. So here it is, you can see the view towards the sun. It is pointing its solar panel in that direction. Then we want to stop this spinning because we want to start taking photos. So we spin up one of the wheels, which is along the axis of the spinning, and then it absorbs all the momentum of the satellite. And now you can see the satellite is kind of like slowed down. Then we activate all 3 reaction wheels, and now they can like very accurately point the solar cell at the sun so that we get our best charging. When it's in eclipse, it goes into this what you call barbecue mode, and when it comes out of eclipse, it starts tracking the sun again. Then now we want to take some photos of the ground, so we use these reaction wheels to point the satellite at the target on the ground, and then it like does a little bit of a broom sweep scan over it, and then it goes back to pointing towards the sun, and then when it goes over the ground station, it points its antennas at the ground station, and it downloads the image that it has captured. This is courtesy of Lawrence Visagie. I'm not sure if he's here. Lawrence, if you're here, just put up your hand. And see Lawrence. Lawrence developed that simulation, which we affectionately called SATVIS, satellite visualization. Okay, so after satellites, I pivoted to aircraft and UAVs. Here, I just want to mention I was fortunate enough to work on some Airbus projects, which Thomas and Ian were very successful with getting projects with Airbus and Armscor, and they had too many projects to do, so they got me in, and I took over the Airbus parts. And we did some interesting projects, which include automatic airborne refueling, automatic formation flight for large aircraft, smart actuators for control services. Chris Japie was working on that. Where did I see Chris? There's Chris. He was working on the smart actuators for control services. Automatic upset recovery for large aircraft, and also fault detection and isolation. So I see I am running a little bit out of time, so I'm not going to explain how the automatic airborne refueling works. I'm just going to show you a video. So my and Thomas's PhD student, Stephen Krill, developed the flight control system to do this automatic airborne refueling, and he had to do it while the aircraft was flying straight and level, in a bank turn, in a race course, and also while they were kind of like descending, which is called a toboggan. And here you can see what the pilot would see in the follower aircraft looking at the leader aircraft. So this required that the follower aircraft put its nose in a very specific location relative to the tail of the front aircraft and keep it there while the connection is made. Then after that connection is made, it should still keep it there, but it was a little bit more forgiving about how much it can move around. It had to do it in light turbulence and in medium turbulence. Okay. Actually going to skip over this one. This is what I did for my PhD, where we automatically recovered the aircraft from stall and spin and unusual attitudes and speeds. So I'm just going to skip over that one and get to some of our UAV work. So some of the projects that I did there was a fault-tolerant control for unmanned aerial vehicles, which was basically we had a aircraft and we would lose parts of its wing and of its tail. So this is called the horizontal tail plane, this is called the vertical tail plane, and that's the wing. And it would lose some of that, and it still had to be able to fly the aircraft and keep it stable. So my student Ryan Maggot, he constructed this aircraft that could pop off its wings and tail, like that. And then we did a flight test where he flew the aircraft in a waypoint navigation style, and then in the middle of the flight he would pop off these things, and then the aircraft still had to keep on flying and stay stable. So there, up there it's flying. You can't really see it very nicely. This is Helderberg Radio Flyers Club, and there will be a picture-in-picture which will show you when it pops off. So it was a big moment. Okay. Then another very interesting, very ambitious project that we did was a series of automatic landing projects. And the one that I'm going to show you, that I show all my third-year students when I teach them control systems, is Paul Moller's automated landing of a quadrotor onto a trailer moving at 30 kilometers per hour. So the real-world application was that we wanted to be able to land a quadrotor drone on the back of a ship, a moving ship, and that ship would be moving and heaving and pitching and rolling. And we demonstrated at least the moving part using a quadrotor landing on the back of a bakkie. So this was now slide 2, which was the quadrotor one. So that's our safety pilot. He's not flying the quadrotor. He's just there in case things go wrong. There is the quadrotor. This was done at Wingfield Air Force Base. Yeah, Wingfield Air Force Base. And we had about 600 meters, I think, of road that we had to accomplish this in. So things had to happen quite fast. And you'll see our very high-tech blue crate that we put our differential GPS in. So you'll see it now soon. There it is. Okay, so the quadrotor has a very accurate measurement of its position relative to the trailer. And what it does is it matches speed with the trailer, and when it figures out that it is now matching speed and it's above the trailer, it descends onto the trailer. So you see it's matched speed, and now it's descending onto the platform. There you go. So that was very impressive. Okay, then I pivoted dramatically from satellites and flight control to energy optimal control for electric water heaters, and that I did with Tinus Boysen, who's also here. And what happened here is we realized that the work that I had done on automatic upset recovery for aircraft, where I did optimal trajectory planning to minimize the altitude loss of the aircraft while it recovered from its upset condition, that same technique could be applied to electric water heaters to minimize the amount of energy used while providing hot water, enough hot water at the right time for the user based on their usage profile. So I'm not going to talk through the whole feedback control system here, but I think some interesting things that you might not realize is there's this age-old question of should I switch off my geyser? Am I saving power? Am I not switching power? And Tinus and I had like a difference of opinion there. Tinus said, yes, we will save power. I said, no, I don't think we'll save a lot of power. And my argument was that because it's a feedback control system, you're only heating the water when you need it to be hot. So if you just have very good insulation, then you won't have losses, and the water will stay at the temperature that you want it, and then you don't need to heat it up, so no energy will be used. But of course there are losses, and the other thing that happens is when you draw hot water out of the geyser, it gets replaced by cold water, which now has to be heated up, but that you need anyway because you want the hot water. So the secret was kind of like to not have the water hot when you don't need it, and to have it hot when you do need it. So what we did is we built this probabilistic water usage model that looked at people's usage patterns and time of day, and then kind of like predicted when the hot water would be necessary. And then we had this optimal control system that decided when to heat up and when not to heat up, so that you have hot water when you want it, but you don't unnecessarily use energy if you're not going to use that hot water. What we also did is, with another student, we wanted to characterize the stratification within a horizontal electric water heater. So we built this sensor array, which Vickers gave us a lot of grief about. But we built the sensor array, and we got in the experts. We got in Joshua Meyer to help us with the modeling and the thermal modeling. And we measured how the different layers in the electric water heater, how their temperatures change when you heat it and when you let it cool down. And then we built a model using differential equations and thermodynamic scientific knowledge. And then we made, determined the constants for that model that would match the model with the experimental data. So here you can see, here are all the temperatures in the different layers plotted versus time. This is the experimental data. There's the simulated data, and there's a good match between them. Okay, I am almost done. Last two projects, which I think are interesting, is I've done, initially inspired by Corné van Dalen, who wrote the initial collision avoidance. Actually, Thomas did the initial collision avoidance at MIT, and then Corné went on with it. And we did these projects on cooperative path planning and collision avoidance for unmanned aerial vehicles in urban environments. Basically what we said is we expect in the future that lots of UAVs will be flying around in cities, and they will all be on their own individual missions to maybe deliver packages or whatever. And they mustn't crash into one another. And the classical way of collision avoidance is to sense the other vehicle and then make a plan to avoid it. But that means everybody has to have a sensor, that a radar or something that senses the other vehicle. So we said, but these are not unfriendly vehicles. They can tell one another where they are, and they would basically measure their GPS positions or in some other way determine their positions and then communicate it to one another. Then they could predict if they were going to have a collision, and then they could together make a plan to avoid the collision. So this has been mostly simulation work, but I had one student, Merrick Hughes, who got this 3D model of New York City's, one of its districts, and then developed a system that takes a slice of the city, builds a roadmap of that, plans a path from any departure point to any destination point, and then if UAVs, that's a long-term plan, and if UAVs encounter another halfway through, then they make a short-term collision avoidance plan. And that collision avoidance plan keeps the UAV as close enough to its original path while avoiding collisions with one another. Then also continuing with the optimal trajectory planning, I optimal trajectory planning for quadrotors with swinging payloads. So here the idea is we have a quadrotor and we have some payload attached with a cable to it, and then we want this quadrotor to navigate an obstacle course of gates while not crashing into the gate with either the body of the quadrotor or the payload. And to make it interesting, we tell it you have to do it as fast as possible, so that it kind of has to swing its payload one way and the other way to get through it, and we use mathematics and feedback control to do that. Last project is we built this hexapod robot, and the idea is to walk over uneven terrain with a hexapod. And here is the hexapod that the first student built. We have a little camera on it that senses the environment around it and then looks what the height is of places where it wants to put its feet, and then puts the feet at the right height. That's what the first student did. What the second student did was to kind of like detect places where it shouldn't put its feet because it's maybe like a hole or a very steep incline, and then choose a different place to put the feet. And my current student, Dani Gous, he's doing blind locomotion, and what he's doing is he's sensing when the quadrotor's, not the quadrotor, when the hexapod's foot hits the ground. So he kind of looks like at he commands the angles of the joints of the feet, but then when it carries a load, those angles aren't exactly what it commanded to be, and by looking at the difference, it can sense the weight that is being carried by that foot. And the result is this. You will see the feet kind of like feeling for when they touch down on the ground, and then so they kind of go slowly, and then when they make contact, they stop. And what is novel about this is it's not using any additional sensors to sense the contacts. Many robots use contact sensors to find out when the feet are put down. This is using just the normal motors that are used to actuate the legs anyway. And again, this looks like a living thing to me. That is the magic of feedback controls. And this looks like some kind of spider or insect slowly, tentatively walking over uneven terrain. Okay, so that's my control systems career so far. I want to conclude by just reflecting and being grateful for the opportunities that I had. As you heard from Prof. Vickers, I had the opportunity to study engineering at Stellenbosch. I had the opportunity to study in the ESL. I studied under Prof. Jan du Plessis, who is a legend in the control systems world. I studied under, or I was supervised by Prof. Herman Stein, who is a legend in the satellite attitude control world. I've had the opportunity to work with experts from Airbus, and they told me how their flight control systems worked. I've worked with people at S-Plane, Sunspace. I've just had so many opportunities to work on interesting systems and with people who know how these things work, and that has shaped me, and it has guided my career. And I'm grateful to my mentors. I'm grateful to Professor Stein. I'm grateful to Vickers, who is also a harsh mentor to me sometimes. I'm grateful to my colleagues, Pietri, my colleagues in the department, and Thomas, who was my lab partner, and then eventually my boss, and my boss again. So I've had so many people who have been role models to me, and I'm very grateful for that. I'm grateful to work with colleagues that are positive and hardworking and care for their students in the department, in the faculty, on the faculty management committee. I'm very grateful for that. And finally, I'm very grateful for all of my students. So when you teach a control systems course, every class you teach is different. The students ask you questions that you've never heard before. You have to think about it. You have to admit that you don't know the answer now. You'll get back to them. So through that teaching, you are learning. I've told people many times, if you want to learn something, teach it. Once you've taught it, then you'll really know it. And I'm grateful for all my postgraduate students who have worked very hard on very challenging projects. I've met with them once a week. I've given them crazy ideas. I've given them sensible ideas. I've pointed them in the right direction, sometimes in the wrong direction. But we have achieved interesting control systems in the process. So just want to list all of the students that I have supervised since 2008. Chris Japie, one of actually my first master student with Jean-Marie, on the top of the list. Stephen, I thought would be here, but I'm not sure if I see him, my first PhD student, and all the way to 2026. I'm very grateful to have worked on interesting projects with all of these people. Thank you very much. That's
Goeienaand, good evening, Moweni. Japie, thank you very much for such a magical lecture. It's not often that we use the words magical and systems in the same sentence here at Stellenbosch. Colleagues, I think it was really a special touch also to see this list of students' names on the board, so that was really special. I want to thank you for this lecture. Of course, I could have done with the crash course prior to having to prepare the rectorate note, but I want to say to you that there's one reflection that I take from this lecture in this topic and in your field, which is very technical, but it's a very human lesson, and that is that life seldom moves in a straight line. Much like sailing, we set a course, but the wind shifts, and the waves rise, and the currents may draw us in unexpected directions. What matters, however, is not that we drift, but that we observe carefully, compare honestly, and then adjust wisely. As individuals and academics and institutions, we continually measure where we are against where we aspire to be. And then we make the necessary corrections and close the loop. In this sense, feedback control offers much more than a technical principle. It reminds us that progress depends on our capacity to learn from the response from the world around us and to remain steady in our purpose as we adapt along the way. Japie, may your work continue to inspire students and your colleagues to observe carefully, to adjust wisely, and to move forward with purpose. And of course, I wish you calm seas, fair winds, and a steady course in the times to come.
So it is my great pleasure to close the loop, Japie. When I had my inaugural lecture in 2023, then Japie did the vote of thanks in my inaugural lecture, so the circle is now complete. I get to do it here. So I first want to start with just giving a word of thanks to different groups of people. The first group is the staff from Corporate Communications and the Marketing Division, Amira, Chuma, Krista, Jonathan Dale, and Justin Alberts for all the arrangements, the recordings, and the live streaming of the lecture. Then special thanks to the members of the rectorate who are here, Professor Nicholas Smith, Professor Sibusi Moyu, and Professor Liesel van Dijk. Then members from the faculty, Professor Wikus van Niekerk, our dean, the chairs of the departments. I have seen some of them here, Johan van der Spey, Nico de Koker, Hubert van Eden as well. And then also to our vice deans and our acting vice deans, Professor Christian Skrewe. I think Professor Celeste Viljoen and Professor Corny Skidder is not here, but thank you to them as well. Then also to the deans, the staff from the Dean's Office who've asked that I do not mention them by name. Thank you for all the preparations to get the venue ready for tonight. Before I continue to the list that Japie has given me, I just want to say something about his impact in our department. So as you can see, Japie is very, very passionate about control systems. This is something that started when he was a student already. So he was final year when I was first year, and then in my third year I had control systems with Professor Garth Milne. This is the same year that Sunsat was launched. So we learned a lot about Sunsat, but not a lot about control systems in our class. And then I would go, and then I was like, we're going to write a test now. So I went to Japie, and then he basically gave me the same crash course that you got today, possibly over a longer period, but you can see he's very, very passionate about that. So he's had an impact as the head of the department of the Electronic Systems Lab when Professor Herman Stein retired and joined CubeSpace. And then he also was undergraduate coordinator. I had 2 EXA visits. He had 3 EXA visits where he was undergraduate coordinator. And now as departmental chair, he's also making a very big impact. The last thing I want to mention about him and the impact he makes is you can really see that he's a selfless supervisor who's committed to the success of his students and to the rest of his colleagues as well. Okay, so now to the list that I got from Japie. I'll go through it as quick as I can. So the first word of thanks, Japie, is to his amazing wife, Marjorie, for her love and support and for their life together. To his 2 beautiful daughters, Mira and Amay, for making him proud and for being here for him this evening. Then to his parents, Japie and Suzanne Engelbrecht, for raising him and believing in him. For our father, for instilling a sense of wonder in him. And for his mother, for teaching him to keep on studying until he knew his work. And also to care about people. He's the nice brother. For his parents-in-law, Ans and Andra Jacobs, for supporting him and always being interested in what he does. For his 2 brothers, Skalk and myself, Herman, who are the best brothers that anyone can have. These are his words, not mine. And with whom he shares a unique common reference. Thank you, Japie. He can also attest that he is the best older brother that brothers can have. To his sister-in-law, my wife, Maria Haan, and his brothers-in-law, Andre and Higu, and their spouses, Inyong and Boram. To Professor Jan Doep, for the many opportunities he created for Japie, for teaching him about the physical interpretation of mathematics and feedback control. For Professor Herman Stein, for whom he learned everything he knows about satellite attitude, determination, and control systems, and who taught Japie to be critical about his work. To his colleagues Corneille van Dalen, Johan Treenicht, Ian Peddle, and Thomas Jones, and Herman Stein, who deepened his understanding of the theory and practical application of feedback control systems. To Tinus Boysen, for the opportunity to work with him on electric water heaters, and for driving Japie to publish. To his colleagues in the Electronic Systems Lab, both past and present, for the strong research laboratory that they have built up over the years. Special thanks to Willem Jordaan and and to Callan Fisher as well. To all the amazing postgraduate students that he has supervised over the years. To his friends and colleagues in the E&E department, academic, administrative, technical, and the assistants, who inspire him and who makes Japie want to come to work every day. So, because take note. To the E&E Departmental Management Committee for helping him run the department. A special word of thanks to the people that makes his life easier as head of the department. Diana Creer, Johan Boysen, Arnold Rix, Willem Jordaan, and Niels Becker. To Professor Pietri Meyer for his wisdom and guidance and for caring about the department. To the fellow HODs and members of the Faculty Management Committee for the camaraderie and for everything that Japie has learned from them. Then a special word of thanks to Professor Wikus van Niekerk for constantly challenging him and teaching Japie not to be too nice. And then to Marley Oberholzer for oral moral support with the preparations and for the arrangements for today's lecture. To the colleagues from Sunspace and S-Plane, both past and present. To the weekly board gaming group for their friendship and the welcome distraction. And then lastly, to all of his friends, family, students, colleagues, and collaborators who came to support him today, both in person and online. And then the last person I need to thank is our honorary speaker, Professor Japie Engelbrecht. So in closing, thank you all for joining us for this evening. And I hope you will all join us now for the great refreshments which is available outside. And then please rise for the academic procession which will be led by Professor Japie Engelbrecht.